Okay, we discuss partial differential equation with Python. So before we go to solve partial differential equation in computer, we need to revisit certain basic ideas and we need to follow certain steps because in computer we cannot directly give the equation and tell the computer to solve because computer can do certain basic operations, addition, subtraction, multiplication and division. So we need to tell the computer that here is the prescription, he follow these steps and do these calculations this way. So this is you can think this is the set of algorithms. Okay, so here we go. This is the first part of this series. So let us deal with the kind of equations which we will call well posed problems. What are well posed problems? The well posed problems often we have encountered in our physics curriculum. These problems come with a set of right kind of initial conditions and boundary conditions so that we have the unique answer for them. So, but fortunately, we will deal those problems only in this thing, and the differential equations are second order partial differential equations, and these are the simplest cases, of course. So, before we move on, let us discuss certain generality of these partial differential equations. Suppose you consider a partial differential equation in terms of x and y. So u x y. So u is the physical quantity, say, and it can be pressure, temperature, density, or any field, or whatever. So we need to see how these vary. So it can vary with x, it can vary with y, it can vary with both. So we have a very general form of the partial differential equation: a del 2 del x square plus b del 2u del x del y plus c del 2u del y square plus d del u del x plus e del u del y plus fu equal to g. So we have all kinds of first order and second order and these terms, differentials, and we have the coefficients a, b, c, d, e, f, g. And among them, let us concentrate on the three coefficients, first three coefficients, a, b, and c. So we can check if b square minus 4ac, if this is less than 0. So for certain kinds of partial differential equations, this holds. These are called elliptic partial differential equations. So Laplace's equation is your this elliptic kind of differential equations. Then parabolic, b square minus 4ac equal to 0. So this is diffusion equation, 1D or 2D or 3D. Here it is shown 1D diffusion equation, del u del t equal to del 2u del x square. Laplace's equation is shown in two-dimensional Laplace's equation. And hyperbolic equation, b square minus 4ac greater than 0. See other kind of differential equation, which is wave equation, del 2u del t square equal to del 2u del x square. So this is hyperbolic equation. So all these in this up until this UG curriculum. So whatever we have faced, the kind of differential equations, whatever we have encountered in physics, this is the three categories. Okay, so you think that in the first Laplace's equation, so they are the derivatives of space, del 2 del x square and del 2 del y square, no time, in 2D. course here. In diffusion equation 1D though, so time it is first order del u del t and the space it is second order. And the wave equation, the time is second order del 2 u del t square and the space is also second order. We could add another term del 2 u del y square, another term del 2 del z square and so on. But to keep everything simple, we will only consider these three very simple equations in our discussions and the following computer implementation of these equations. Okay, so before we move on, before we tell the prescription to the computer, that means the set of rules, set of steps to computer how to solve the differential equation, we need to uh, discretize the equation because the computer does not understand differentials. So to discretize, so let us have u is a function of x and y. So you tell expand this in terms of x. So if you write on the left u x plus delta x comma y equal to u xy plus delta x del u del x plus delta x whole square by 2 del 2 u del x square and so on, all these terms. So this is a partial expansion in terms of x. So you have done this Taylor series in your life many times. So in this expression, if we discard the term second order onwards on the right, so the term involving delta x whole square by 2 delta x whole square and by 2 into delta u del x del 2 u del x square and so on, this term onwards, the second order term onwards, if we discard them, then we have a very approximate formula of del u del x, which is u x plus delta x y minus u x y by delta x. So you can think that this is a very well-known Eulerian scheme, just the difference between two u's by the difference in x direction. So that is your del u del x. So precisely this is Euler method that you have done in your ordinary differential equation when you solved Euler method through Euler method. Okay, so this is your del u del x. Next, similarly, you can also write del u del y kind of approximately equal to u x comma y plus delta y minus u xy by delta y. So this is the same way. So you expand u x plus x comma y plus delta y in terms of partial expansion in terms of y. So you get the similar formula. In these two formulas, we call forward difference method. The entire thing that we discretize a partial differential or a differential in terms of some finite difference. So this whole exercise we can carry on later. So the whole exercise is called finite difference method. If you see your if you have ever read this chapter in your math method book or any numerical methods book, you will see this is a standard method, and you can do with this, you can follow this scheme, very simple scheme, and you can arrive at the formulas, discretized formulas for all kinds of differentials. Okay, so this is basically finite difference method for you. Okay, so let us say h equal to delta x to symbolize. Okay, so you write u xi yj is equal to u ij. So just to make it things look simple, and you remember, you think that I is the x index and j is the y index. So imagine you were standing on a square network or a graph paper where I and I comma j is the position. I say I takes integer values 1 2 3 4 and j takes integer values 1 2 3 4. Okay, so on the horizontal axis I takes 1, 2, 3, 4, and the vertical axis j takes 1, 2, 3, 4. So you know where you are. You sum at ij point. So any xy point can be replaced by ij point. So that's why u xi ij yj, that can be replaced by u ij symbolically. Okay. And also on the right side you see u xi plus h. That means you have increased xi by delta x in the x direction, and this you call ui plus 1j. So the effect is that if you write in this symbolic form, that means your x direction, your the index is increased by 1. So you have discretized the formulas so that you go discretized step in x direction and also in y direction. Okay, so that's how we write uij ui plus 1j. So with this, the formula looks del u del x ij equal to 1 by x ui plus 1j minus uij plus the rest of the term. We clump all those in OH. OH means the error you incurred is order of H in this forward difference formula. Why? Because you have discarded second order terms onwards, and there it was delta x whole square, and you delta x means H, and you now in this formula divide by H. So the rest of the terms, the leading term will be of H, and then again H square, H cube, and all those terms will be there. But since you know H is the difference in x, and H should be less than 1, because you take very small step in magnitude. So if delta x, if H is less than 1, so H square is even smaller, H cube is even smaller, and so on. So the leading term with error, which contribute in the error, is of the order of H. So that's why you write in this way. So the forward difference formula in this discretized Eulerian scheme, to what you have got is that some error in H, okay, order of H. Next, similarly, you can find out del u del x in terms of, it is a little different way, uij minus ui minus 1j plus order H. This is called backward difference formula. What is the difference? Forward difference means you are standing here at the ijth point, and you are looking forward at the I plus 1th point on the x-axis. So you take the difference between the forward value minus this value. And the backward difference means similar difference, but you look backward. You are standing at uij, at ij, and you look backward, previous point, I minus 1j on the x-axis. So you take the difference between those values. And the x step, the delta x is same for all, same for in two cases. But you do this in a little different way. So this is called backward difference formula. So the first order derivative del u del x, you can choose any of the formulas, forward difference or backward difference, and the error involved in any both of them is the same order of H. But we will see in while we will do in computer, or people do in computer, we will see that what is the advantage for us, whether we will take forward difference formula or we will take backward difference formula. For that you need to look at the final formula, and need to look at how the computation is done in computer really. Okay, so let's see ux plus delta x comma y. So this Taylor series expansion ux plus delta xy, and also you Taylor series expand of ux minus delta xy in the similar way. So the plus minus negative, the alternate plus minus terms will come, and you take the difference between these two expressions. You will see on the right side will be 2 delta x del u del x plus delta x whole cube by 3 delta cube del cube u del x cube plus, and so on, dot dot dot. So in this difference formula, if you on the right side, if you again discard the third order term onwards, you will arrive at a formula del u del x equal to approximately equal to u x plus delta x comma y minus u x minus delta x comma y by twice delta x. So the same expression, finite difference formula, but in a little different way of del u del x looks little different. That means you are in this expression on the right side, you notice you are standing at xy point, but that uxy is not needed to calculate here. You look forward on the x plus delta x and you look backward x minus delta x. Those two terms are used here. So this is a centralized formula. This is called central formula because you stand at the center and you use the value of u on the forward direction and value of u on the negative direction. And this is this formula. Let us see if we write in terms of the indices. 1 by 2h ui plus 1j minus uij, and the order of the error will be of course h square, because you see the third order term delta x cube means h cube you have discarded onwards, and so you divide by h means delta x, and the order will be, the leading term will be of the order of h square. So the formula now we have derived with central difference formula, the order you have seen suddenly have the error is minimized because the error is of the order of h square. Of course, remember h is less than 1, so h square is even smaller. So this is called central difference formula. So now you know the same first order partial derivative, you can calculate this in three different ways: forward difference formula, backward difference formula, and central difference formula. Okay. Similarly, you can arrive at another formula. If you take u x plus delta x y, you take the Taylor expansion of this term, then you add with it u x minus delta x y, Taylor expansion of this term. Like that, you on the top you did, you subtracted, now you add. So the other terms will remain. That means you will have 2uxy, the zeroth order term, plus the delta x whole square del 2u del x square, the second order term. These two terms onwards, the alternate terms will remain. Okay. Now you don't discard the second order term, because in the previous example you discarded the third order terms. So you will keep the second order terms, and that will give you the formula of second order partial differential. So now you can easily check that del 2u del x square at the point xy has the formula u x plus delta x comma y minus u 2u xy plus u x minus delta xy by delta x whole square, right? So in the symbols of ij, you write ui plus 1j minus 2uij plus ui minus 1j plus h square. So this is the formula of second order partial differential. Of course, this is central difference, and the order of the error will be the same h square. Similarly, you can calculate del 2u del y square, del 2u del x del y, and so on. So that tells you the entire scheme in short of finite difference method, how you can discretize all the partial differentials, any kind of mixed term, pure terms, and so on, and you arrive at a discretized formula of a particular partial differential equation. So we now discuss diffusion equation in 1D, diffusion equation in, say, in U. So you write this very familiar differential equation, del u del t equal to d square del 2u del x square. So d is the diffusivity, and you note that this problem is defined on a finite system. That means you need to see the diffusion on a finite system. So x it varies from 0 to L. So x is bounded between 0 and L. You can imagine a line which extends from 0 to L, or a rod where heat flows between one end is 0 and another is L. L is the length of the rod. And to solve it, because it's a well-posed problem, to solve it, you need to have one initial condition, ux0 equal to u0x. X0 means the time is 0, and you give the say temperature. If you use the temperature, you give that temperature at all points of x to begin with. So you right side you write only function of x, right? So at the initial point, at the initial to begin with, initial time, you give the function, you give the values of which is function of x. That means you are giving at all points, you know it. Then you see how they evolve. Okay, so this is the initial condition, and you write the two. You need two boundary conditions. Boundary condition means the conditions at the boundaries. That means in this case, this is a particular one-dimensional case. You need two boundaries. You have two boundaries, left hand say and the right hand, and those conditions will be fixed over time. That means that is valid for any time. So symbolically, you write u0t equal to u1t. Okay, and you write ult, that means the other end, say right hand, that is u2t. So you see the right hand, these expressions are all functions of t. That means whatever you give, that will be constant over all the time. And initial condition, whatever you give at all the points, that will be function of x only, no time. So it with time it will change. Okay, so that will be given by that change will be by the differential equations. Okay, so this is your diffusion equation, complete description of the diffusion equation in 1D. Okay, but you have to remember that this is a very simple form, because you have not allowed radiation or Newton's cooling from it. So you think if you think of the heat equation, then you have to think that this is valid for a purely insulated rod. Okay, so let us write this equation, the same equation in a discretized form. Del u del t. You see, we write del u del t with the forward difference formula, and you see on the right side we have changed the notations in a certain way, because look at the power, the topmost, this u I j plus 1. So the superfix j plus 1. J is the now time index. So in order to differentiate time and space, we have put the time on top, so that later u can be function of x, y, z, t, and we can modify this formula so that the time will remain on top, and the suffix you can write I, j, k, etc., etc., all the indices. So this is forward difference formula for u. K is your delta t. Instead of u x y, you have written here, you have here u is a function of x and t. So if you discretize del u del t with forward difference formula, so it will look like u I j plus 1 minus u I j. That means you have taken difference between forward time and backward time. Okay, and the order of the error will be order of k. But you can ask immediately why this forward difference formula, because there is also for backward difference formula, and most importantly there is central difference formula. But you know, the more you go into the depth of this solution of these problems in computer, you will see in certain times we have to be less ambitious, because the practices in this formalism, in this kind of solution, to be simple, we try to make things simple, so that we write del u del t in forward difference formula, and del 2 del x square, of course, you have taken with central difference formula. Because why two different things? Because the ultimately with this discretization scheme, uh, whatever the formula will arrive, that will be easily solvable. That is one point. And then of course there will be later investigations of stability and all other things. So be happy with these two kinds of discretizations, different that something different kinds of discretizations. Okay, so you look at the del 2u del x square, ui plus 1j minus 2 uij plus ui minus 1j by h square. So you understand, see, you understand this on the second formula. So superfix j has not changed, but the suffix I has changed. So it is obvious. Okay, so the in this form of discretizations of the from the two formulas, you have incurred the total error is order of k plus h square, right? And remember, I is your space index, j is your time index, right? And so the discretized formula now looks like this: uij plus 1 minus uij by k is your delta t, remember this, and equal to d square, ui plus 1j minus 2 uij plus ui minus 1j by h square, right? So what is your d? D for a rod that you are hitting for the heat propagation so you may consider that d is the equal to root over of k by 0. In a problem you can be given some k, c and rho. K is the thermal conductivity, c is the specific heat, rho is the density of the material, and you can set the problem in such a set the scale of the problem in such a way that you can take d equal to 1. Okay, so in computer, so you can take in arbitrary unit and scale. And the since d is 1, you can think the left from the left side denominator, the k can go on the right side. So the right side prefactor will be k by h square. So you can have the ratio of k by h square on the right side. So that you can call sorry, r. That you can call r. So r is equal to k by h square. That means delta t by delta x is whole square. But you can immediately recognize that delta this k and h are not in your control. So it is the ratio of these two things, that is r, that will be should be controlled. Okay, so the formula now looks like uij plus 1, that is the value at j plus 1th time, equal to uij, that is the value of at the ith point at the jth time, plus r into the rest of the terms. So look at the right hand terms and the left hand terms. In the left hand you have this, look at the top indices, I mean superfix fix. So it is j plus 1, that means the left hand term is a evolved, you have evolved this term, you have evaluated this term at the j plus 1th time, and on the right time every term is of the previous time. So in this particular scheme, this time this kind of scheme is called explicit scheme. That means you know immediately the j plus the new time, the value at the new time by the values at the old time. So you need to know only three values of the old time: ui, ui minus 1 and ui plus 1. That means where you were standing, forward direction, backward direction, and these three terms you need, just nearest neighbor of ith. Okay, so what is now to decide about r? See, this set of you see you will have a linear algebraic set of equations. To solve them for different psi and j's, to solve them, you if you follow the von Neumann stability analysis criterion, we won't describe this here, but you can follow any good numerical method book, Scarborough, SS Sastry, then there is a very good book, Numerical Recipes, and all other books for your curiosity and to satisfy yourself. that if you analyze these kinds of equations, so you have for the eigenmodes to be stable, so you need to consider the value of r between 0 and half. So in the most of these simulations, most of the numerical calculations people take the value of r between 0 and half, and most commonly people take r equal to 1 by 4. That is, you have to understand the value is chosen for convergence of the for the solution. Okay, so you take r equal to 1 by 4, we take r equal to 1 by 4 for our further calculations. So the now the formula now becomes, in the red, uij plus 1 equal to uij plus 1 by 4 ui plus 1j minus 2 uij plus ui minus 1j. Right. So this is the formula we are going to implement in computer. That means we are writing a program or script with Python with this formula, and you immediately recognize that this formula is a kind of is a recursion relation. You have encountered very many recursion relations like Fibonacci chain and so on that you solved in your initial when you learned Python or any computer program. So this is a recursion relation, and this scheme, this formula often is known as Smith method. Of course, this is an Eulerian scheme, and you should know that there are very many methods. Like there are Lax's method, there are Lax-Weinrop method, then there are Lassonen method. See, in this formula you have used forward difference for the time and backward difference for this. I mean, certain central difference for this space. In the Lassonen method, for example, you take backward difference of time and the forward, the central difference of space, and we take the average of these two different kinds of formula, and then you can arrive at the another formula, which is very famous, another scheme which is called Crank-Nicholson method. So very famous. So for your future kind of learning, you can explore all those kinds of formulas. Basically, those are the variations and combinations of very different ways of discretizing the differentials. Because you discretize the differentials and you have to see whether you can solve it in computer. For explicit form like this, you can solve easily in computer, but then if you do say Crank-Nicholson method, then the formula will become some implicit scheme, and it will have to be solved by the solution of tri-diagonal system. Why tri-diagonal? You can understand, because I plus 1 and I minus 1. Okay, so there are very many different kinds of schemes with which you can solve these kinds of discretized formulas, implicit, explicit, whatever. Okay, so here we go. So remember, r equal to k by h square equal to 1 by 4, and with this we can choose any combination of h and k. Say h equal to 1 by 3, k equal to 1 by 36, it will satisfy this, for example. So imagine the problem. This is one insulated rod, and the ends are fixed at the, say, temperature bath. Fixed means temperature bath means it can be, you can put the two ends at the ice bath, that means 0 0. You can put the two ends at the steam, that means 100 100 100 or so on. You can, this is up to you, is your problem. And imagine the length of the rod is 1, and the boundary and initial conditions you can write in this form: u x t, x is 0, so the left end of the rod, so x 0, and time is any time, so u 0 t you can put it at 0. u 1 t, because the length of the rod is 1, it can be 1 meter or so. u 1 t equal to 0, this is another boundary condition on the right. And then you can write u 0.5 comma 0 equal to 1, so this is your initial conditions. 0.5 means you put at the middle some value of temperature which is 1. Okay, so this can be your one set of one problem. So description of the problem in the simple terms. To see it pictorially, you can think, if it is visible to you, the figure. This is a rod, left and right are in temperature bath, and you immediately think of discretizing the rod. So we immediately think in terms of Python. So you begin to mark the different equidistant points on the rod as 0, 1, 2, until 100 at the last point. Okay, so these are the points 0, 1, 2, 3 up to 100, and so there are 101 equidistant points on the rod, say. So now you can translate the boundary and initial conditions as in terms of, say, u is your, say, one array of numbers. So u can be anything. U is your physical quantity now, but u is an array in computer. So u square bracket 0, that means on the 0th position it is 0, and u at the 100 index position it is also 0. So two boundaries are now fixed. And say at the middle 50th position, 50 is not the distance, 50th position, 50th index, so that is 1. So heat is delivered at this point. This is the initial condition. And you can look at this network also, if it can help you understand better. So on the y-axis this is time evaluation, and the x-axis the rod is lying. So you at the bottom line you see it is time equal to 0. Next level, next horizontal line, it is t equal to 1, and then it's t equal to 2, and t equal to 3, and so on. You can imagine that way. So the bottom line you have I, and then right you have I plus 1, then left you have I minus 1. If you go to the next level, means next time step, you can evaluate I there, the value of at the ith position. For that you need to know I minus 1 and 1, I and I plus 1, the u at these three positions at the previous time step. So that is how you do in computer, and you can imagine it this way. So now I write the program in a very simple form. You can write your own program, but I just show it for the demonstration purpose. I mean, it is better to write your own program, and you must write, because writing a program is an art. So, and the art is, the style and art is very sometimes it's a very personal thing. Although you follow the algorithm, but the way you write, it's up to you. I show one kind of implementation, you show another kind of implementation, that is up to you. And then you play with all the boundary conditions, arrive at the results, and so on. So this is Python script for diffusion in 1D. You need to import NumPy as np. You need matplotlib, import matplotlib.pyplot as plt. You need to define the rod, the space. So the it's already a NumPy array, x equal to np.linspace. It goes from 0 to 1, comma 101. That means you have created 101 points from left hand to right hand. Okay, this way. And you have u equal to np dot zeros. This is a special NumPy array array. You have already, probably you know. If you don't know, you can put this on your computer, on your interpreter, and can check what this gives. np.zeros gives you, and in bracket there is 101. That means all 101 points you have given zeros. That means you have an array of 101 points for which all the elements are 0. So that's your u. That means including the first and the last, beginning and the end, including two ends, you have put the temperatures at all the points 0. The difference between the only difference is that the last and first points you don't update them. The rest of the points you update. Okay, and this is probably, say, initial condition. This is initial condition. That means at the middle u50 you give 1. You can give any value. 1, I just give 1. So unit does not matter. So it's a delta function probably. Okay, so now you do this for time in range, say 100. So you do this numerical evaluation for the time step of 100 time steps. Okay, and you see u is we have described u as a one dimensional array, but you can have two indices, two things x and t, but intentionally we don't want to know thing at each time step. If we want to know, you will modify the program. For it to be simple, we need to know what is the distribution of u along the rod after certain time step. So for that we write this program. So after that there is a loop on space, loop on x. So for I in range, all the points between 1 and 100 means you don't touch 100. So it will update the points from 1 to 99. So it will leave out 0, 0th point, and the 100 point, because these two ends are at temperature bath and should be kept free, fixed. Okay, and you just write this expression ui means the value of u at the position I plus equal to, meaning ui equal to ui plus the rest of the terms, ui plus 1 minus 2 ui plus ui minus 1 by 4. I have written 4 floating point. Okay, so this is all you have to do to implement the discretized scheme and to iterate over all the positions on the rod and to know the values after a certain time. So this is all you have to do. So we have not used explicitly the time index in the arrays, because to keep things very very simple at the beginning. If you want, you can do that, and you can complicate your program the way you want. But my philosophy is to write a program that is as clean and as simple as possible. Okay, so now the next task is to come out of the loops, and then you plot x versus u and see how you have become, because you have given imagine a rod where all the points are 0 and at the middle it is 1. So now how the temperature spreads all over the rod after a certain time. If you now write plt.plot xu and then necessarily plt.show, if you write on your interpreter, then you can see the graph. So this is but further you can further simplify this program with your Python machinery. Suppose this thing for I in range 1 to 100, you write these 2 lines. Even you can minimize this. You imagine if I equal to 1, then ui means u1. So the left side it starts from 1, and the right side ui plus 1, that means it starts from u2, right? And the last term, it is ui minus 1, that means it starts from u0. 0 means the left boundary, but it won't update that, but it will use the information from that. Okay, so these 2 steps can be thought of as you do this thing again and again. You start from 1, then go to 2, 3, 4, 5, and then again so for I equal to 1, you need 0th term and second term. If for I equal to 2, you need previous 1 term and the next index of 3 term, etc., etc. So you can think of that doing this again and again means basically you are manipulating the array. That means you can write it by NumPy slicing that you have learned in your NumPy class. Okay, so these 2 lines can be written with a simple NumPy slicing. You see, on the left side you have the for loop should go from 1 to what? 1 to last but 1 term. So that means you have written u1 colon minus 1. It will start from 1, and the minus 1 means this last term, but it won't touch the last term. And on the right side, instead of 1 by 4, I write 0.25, and then you see the first term ui plus 1. That means it should go from 2 until the last, right? 1 step ahead. So it will go from u2 colon blank. That means it will go from 2 to the last term, and so on. And the last check the last term u colon minus 2. Minus 2 means, I mean, the colon blank colon minus 2, that means it will start from the beginning, because it will start from the 0th term and it will go up to uh, before the minus 2 term. Minus 2 means the minus 1 is the last term, then before that minus 2, and then don't touch minus 2, but it will come before that. Okay, so this is this way. You, with this inclusion, with if you include that thing, so it is not only the simplification of the steps, but with numpy arrays you do better, because if you want to write the, if you write to it, want to iterate this loops for many times, so you want to have a large numerical thing, large time, you want to run it for large time, so this time matters. So but the numerical, this numpy slicing does it very efficiently. So if you think for a bigger simulation, bigger numerical calculation, you should adopt this kind of mechanisms, machinery. Okay, so with this the program now becomes everything else is the same. Only thing is that you now have a even more simplified form, the program, the Python script, which for you need only one loop for time in range 100, and the rest is with Python numpy slicing. Okay, so and then plot these and then see this. Okay, so we stop here at this for this episode, and on the next episode we will discuss various boundary conditions, and we'll see the how the result comes out, and we'll compare with exact solutions, some exact solutions, and then we later we will extend this discretization scheme for two-dimensional diffusion, and also solve that and see 3D plot. Okay.